Welcome to the basics of electricity. Electricity is a rather vague term, so we will be using terms like current, charge, voltage, and resistance. When we think of electricity, we're really thinking of the flow of electric current, and we need charge carriers for current to be flowing. Usually, current flows in metal wires, and all metals have a similar structure. Here is that structure. These positively charged atoms are positive because they have lost the outer shell of electrons, and these electrons can move around inside the metal wherever they like. This makes them excellent conductors of electricity as well as heat. If we were to put a large positively charged plate at this end and a large negatively charged plate at this end, then the negatively charged electrons would be repelled from the negative plate and attracted towards the positive plate. All of them would do this. And therefore we would have an electric current. These charged particles are the charge carriers. They carry charge through the circuit. These electrons have a charge of negative 1.6 times 10 to the power of negative 19 coulombs. That is fixed. Every single electron has this charge, and that cannot change. Charge carriers are not always electrons. Sometimes they are positive or negative ions in a liquid. For example, if you melt or dissolve salt, then the individual sodium and chlorine atoms become a positively charged sodium and a negatively charged chlorine. These, when they are either dissolved or melted, but in a liquid form, can be charge carriers because they are charged atoms capable of movement. And if you put a positive electrode and a negative electrode into that liquid, then the negatively charged chlorines will end up at the positive electrode, and the positively charged sodium will end up at the negative electrode. You will study this in chemistry in electrolysis. Electric current is represented with the capital letter I. It is measured in amps, and we use the capital A for amps because it is named after a person. Current is the rate of flow of charge. Whenever you have a divide by time, then it is the rate at which something is happening. We know that time is measured in seconds, represented by a lower case s. And the delta means the change in time. So we take the amount of charge that has gone past and the time that it took for that amount of charge to go past. The charge is measured in the unit coulombs, which is represented with a capital letter C, again because it is named after a person. And that is represented with the letter Q. You may see Q as a capital, you may see it as a lowercase. In equations where two charges are being considered, then you may see the capital Q representing the larger charge and the lowercase q representing the smaller charge. But in this equation, we tend to use the capital. Some students will say that the current is moving very quickly. This is not correct. Current depends on several things, including speed. If we have a look at a conductor, then in order to calculate the current flowing through that conductor, we need to know how many electrons there are available to carry the charge per meter cubed in that conductor. We also need to know the cross-sectional area of that conductor, measured in meters squared. Then we have the velocity that the conductors are moving, the average velocity called the drift velocity, and that is measured in meters per second. And finally, we need to know the amount of charge that is carried by each of those charge carriers, and that is measured in coulombs. If we analyse these units, we can see that meters to the power of -3, +2, and +1, they cancel out, leaving us with seconds to the -1 and coulombs. Seconds to the -1 and coulombs. So we could say that these two equations are equivalent. They both equal current. But you'll notice that current is not the same as velocity. Velocity is important in the calculation, but so are many other things as well. One of the most important rules that you learn at GCSE is Kirchhoff's current law. Here is Kirchhoff, Gustav Kirchhoff, who lived in the 1800s. He did a lot of work with heat as well as electricity. Kirchhoff discovered the way that current behaves at junctions. If you have a wire coming into a junction and two wires leaving a junction, then the sum of all the currents entering and leaving must be 0. Essentially, current flows like water in a river. If you have water coming in and it splits, then it must split in such a way that the two currents coming out sum to produce the current that went in. This equation over here works because current is regarded as a vector quantity. So you would say that you have +5 amps entering the junction, and then you have 2 amps leaving the junction. So you would treat that as a negative, and then the 3 amps here is also leaving the junction, and that equals 0 amps. Voltage is represented by the capital letter V. Capital because it's named after a person. And voltage is defined as the work or energy done per unit charge, which is Q. We measure voltage in volts, which is also represented with the capital letter V. This can be quite confusing, but you must try very carefully not to use these two terms interchangeably. Work is the amount of energy carried by the charge. So in the wires, we have our charge carriers moving, and therefore we have a current. And as these charge carriers move, they are carrying energy, and they are capable of doing work. And the amount of energy that they are capable of carrying per unit charge is the voltage. If we have a circuit with a power supply and a resistor, then we have two types of voltages. We have the voltage of the power supply, in this case a cell, and we have a voltage across the load, the component or components in the circuit. We can measure voltage using a voltmeter. That's why we say we measure the voltage across, because the leads must be connected either side. But you will notice that the voltage of the power supply is equal to the voltage across the load. And this is because of the two types of voltage. We have EMF, represented by an epsilon, and that is energy that goes into the circuit per unit charge, and we have potential difference. Usually written PD, which is energy coming out of the circuit. So the power supply provides energy to the charges, and we have the charges delivering that energy to the components, and that is energy coming out of the circuit. And you'll notice that the energy per unit charge, or the EMF, is the same as the potential difference, the energy per unit charge that is coming out of the circuit. Energy is being conserved, which is one of the most fundamental laws of physics. Here are some of the people we've been talking about. Charles Augustin de Coulomb, after which we have the unit Coulomb, was a French physicist. Notice that when we write the unit Coulomb, we write it with a lowercase letter at the beginning. When it's a name, it's a proper noun, so we use a capital. But unless the unit is at the beginning of a sentence, we don't do that. We have the Italian Alessandro Volta, who invented the first ever electric battery. The Frenchman André-Marie Ampère, after where we get amps. Notice that the unit, when written after a number, is a capital letter when it's named after a person. We don't get that with other units, like meters. Both Ampère and Coulomb are French, and their names are celebrated on the Eiffel Tower. If you visit, look up and see if you can see them. And finally, we have George Ohm, after which the unit of resistance is named. Resistance, represented by capital R and units ohms, is a measure of how difficult it is for the electric current to pass through. If resistance is very high, then we need a large voltage to push the current through. If the resistance is very low, then we don't need as big a voltage to push that current through. Resistance is voltage divided by current. And if we substitute in the equation for voltage, which is work per unit charge, then we find that we can represent resistance like this. And when you study internal resistance, we will be revisiting this relationship. But fundamentally, what this equation means is that resistance is a description of the amount of work or energy that is being transferred inside the component that has resistance. And when we look at a resistor, the function of a resistor is to transfer electrical energy into heat energy, which means that work is being done. A resistor is quite a simple component. A resistive conductor is wrapped around an insulator and then covered with another insulator. We can see in this diagram that the top layer of the insulator has been worn off, This resistor has fewer loops than this one, and even fewer than this one over here. If we use this guide on the right-hand side, then we can use the colours that are painted on the outside of the resistor to give us its value. And we predict that with fewer loops, this resistor will have the lowest resistance. So we have red, purple, black, and gold. Red represents the number 2, purple represents the number 7, and black gives us how many times you need to multiply that figure by 10. And it looks like we're multiplying it by just 1. So this resistor has a value of 27 ohms. Here we have orange, orange, brown. So orange is 3, 3, and brown tells us to multiply it by 10 once. So the middle resistor is larger, 330 ohms. And then finally we have orange, orange, green, orange, orange, and that would be multiplying by 100 kiloohms. There's the 100 kiloohms. So we could write this as 3.3 megaohms. Here we have some other combinations. Pause the video, have a go at calculating them, and then I will reveal the answers. And here they are. Notice that there is another colour. These gold bands on these resistors here tell us the tolerance of the resistor, which is plus or minus 5%. When resistors are manufactured, they're sold at discrete values. So you manufacture a resistor and then you sell it either with a plus or minus 5% tolerance, or give it a silver band or plus or minus 10% tolerance. The silver banded resistors are usually cheaper than the gold banded resistors. You can also get smaller tolerances. You don't need to be able to identify resistor values from the colour banding as part of your A-level, but it's potentially very useful.